Let's look at another example of graphing a rational function. Here we're going to work with f of x equals x minus 3 over x squared plus 4x plus 4. And I'd like to apply our procedure from class, our graphing rational functions procedure. So we're going to go through the steps as outlined on this handout that's posted in Canvas. And so here we go. So the first step that we look at here is to check for the vertical asymptote, which I abbreviate VA. What we got to do is set the denominator equal to 0, right? As long as the fractions in reduced form, this will work, and ours are always reduced. So if I set that denominator equal to 0, x squared plus 4x plus 4 equals 0. Can we factor here? Yes. This is not hard to factor. X plus 2, x plus 2. Actually, both factors are the same. So we only have to solve x plus 2 equals 0. X equals negative 2 is our vertical asymptote. So on my graph at negative 2, I know to put my dotted line for a vertical asymptote. And then we're going to have to figure out which one of the 4 behaviors our function has. It's either going to have this shape, this shape, this shape, or this shape next to that vertical asymptote. And we don't need to figure it out right away. Let's get some more information on there and some points plotted. Number 2, step 2, is to check for the horizontal asymptote. Here, the degree of the numerator is less than the degree of the denominator. So we can say numerator degree is less than denominator degree. And in that case, on our sheet, if the degree of the numerator is less than the degree of the denominator, we know the x-axis, y equals 0, is a horizontal asymptote. So the x-axis, also known as y equals 0, is our horizontal asymptote. So I'm going to just line up my ruler here. And just so it shows up, I'm going to put it slightly off. Dotted line for the horizontal asymptote. Okay. Step 3 is to look for the intercepts. Let's see, f of 0. If I plug 0 into the function, I get 0 minus 3 over 0 squared plus 4 times 0 plus 4. That's negative 3 over 4, or negative 0.75. So 0, negative 0.75 is my y-intercept. So 0, negative 0.75 is about there on this scale if each square is 1. And for my x-intercept, if I set f of x equal to 0, I'm setting x minus 3 over x squared plus 4x plus 4 equal to 0. And the only way that can be equal to 0 is if the numerator is 0. Or you could multiply both sides by the denominator, and you're going to end up with that numerator equal to 0. So we get x equals 3. And so 3, 0 is the x-intercept. I only have 1 here. 1, 2, 3, 3, 0. I have that point here. Okay. And step 4 is to check to see if the graph crosses the horizontal asymptote. And that can happen. And so the way we verify that is we set the function equal to the horizontal asymptote value. That's the y equals 0 value. So we'd set f of x equal to 0 and solve. But we've already done this. So here it's the same as the x-intercept. It just happens to coincide with the x-intercept because our horizontal asymptote is the x-axis. Okay, so we actually already have that point. It's the same as our x-intercept, our 3, 0. So that's useful information because that's the only point where the graph can cross the horizontal asymptote. Okay, now let's see if there's anything we can say here based on what we see so far. I mean, I kind of imagine I'm going to connect these guys up somehow. And now I have to cross that horizontal asymptote at 3. I have to rise above it. As I move to the right, the graph, I don't know how high the graph rises. I'm probably exaggerating this quite a bit. But it's going to have to settle down and approach that horizontal asymptote as I move to the right, as x becomes very, very large. There's just no other possibility there. This lump, I probably exaggerated. If you were to check this graph in Desmos, I bet that lump would be almost imperceptible. But we do rise a little bit above, and at some point we settle down and just start approaching the x-axis when x is very, very large. When x is very negative, we're also going to be approaching that horizontal asymptote, but I don't have too much to work with over there. So I'm probably going to end up plotting some points for x values less than -2. In fact, I don't think it's that hard to plug in -1. If I evaluate the function at -1, f of -1, I did that ahead of time, is -4. -1, 1, 2, 3, 4 is right there. I need, well, let's maybe just look at the behavior around our vertical asymptote here. I think we can see the graph is turning downward, and I would suspect the graph is going to come plunging down along that vertical asymptote. I mean, it pretty much has to. It can't turn around and rise up higher because it would have to cross the horizontal asymptote again, and we know that can't happen. I'm going to put a few more points here on my table just to verify that. So when x is equal to -2, the function is undefined. That's why we have a vertical asymptote there. If I look just a little bit to the right of -2, a little bit larger would be -1.9. On the other side would be -2.1. I went ahead and evaluated the function at both of these points ahead of time. I just plugged in and used a calculator to figure it out. At -1.9, I got -490. Woo. And at -2.1, I got a y value of -510. Well, that -1.9, which is just to the right of -2, gives me a very negative value. So it's clear the graph is just plunging down right there. And I'm not done. So I have this portion of the graph from here to here to here, up and around over to the side. But I sometimes will see students who will turn in this as their final picture, like they're done. And there's a problem here. We need to plot points for x values less than -2. The only x value that does not have a point is -2, where the vertical asymptote occurs. The domain of this function is all values of x except -2. So there should be a point plotted for every x value on your x-axis except where there's a vertical asymptote. The graph never crosses the vertical asymptote. So I gotta look at what's happening to the left of -2, and I'm going to make a little bit more room here for some more values. I probably would just plug in and plot some of these to get an idea of what's going on, like when x is -3, -4. How many you plot is up to you, as long as you can get the shape of the graph. When x is -3, when I plug in, I got a y value of -6. So -3, 1, 2, 3, 4, 5, 6. When x was -4, I got -1.75. For y, -4, -1.75 is like between -1, -2 on the y, about there. So it certainly looks like to the to the left-hand side of the vertical asymptote, I feel like I'm plunging down here, and at that -2.1 that I already calculated, I have a very, very negative value, so that makes me feel very comfortable drawing this graph plunging down. Notice that of the 4 possibilities around the vertical asymptote, for this graph we actually have this 4th, where on both sides the graph is plunging down to -infinity. Now I still got to continue the graph to the left, and there really aren't too many choices here, because I could plot some points, but I know I have to approach the horizontal asymptote, and I also know I can't cross it. So I'm very certain that the graph is going to do something like so. It's going to stay below because it can't cross. I can't have another x-intercept. I don't have another x-intercept. And make a nice smooth curve out of it. There we go. So we got two pieces to the graph. You kind of get a piece on each side of the vertical asymptote. One has this like wiggle to it where it crosses the horizontal asymptote, the x-axis. I probably exaggerated that lump. If you were to check in Desmos, that wouldn't be so noticeable, but it's there. On the other side, we don't cross at all, and we got it. There's our graph.